Hello people, so we are in chapter 6, chapter 4, section 6, coordinates and change of basis. We are going to start with an analogy so you understand exactly what's going on. It's very simple if you understand what's going on. So we have here our dear puppy, dog, and the idea of the entire section is to have different words that represent the same dog in different languages. So the idea is to find the coordinates or the words in different languages for the dog. So language will be our basis. You know that every linear space has a basis, actually has infinitely many of them. So as soon as we change basis, coordinates of people living in the linear space change. So here our puppy is one guy living in our linear space, and the basis will be a language. So we change the language, we change the basis. The coordinates or the words will change depending on the language. So that's the idea of the intersection. It's very simple to understand. Now what we would like to do is to build kind of dictionary if we want to go from English to Spanish to translate as many words as possible, not just one. Then we will need a dictionary. Well, dictionary in linear algebra will be our transition matrix from English to Spanish. So basically we are going from one basis to another using transition matrices. So another example using linear algebra actually is if we take 0.22, that's our puppy, and we express 0.22 in different coordinates depending on the basis. So if we use a standard basis, canonical basis, well, coordinates of 0.22 are still 22. But now if we change a basis for basis 1103, then the coordinates of the same point, same location, will be 2 and negative 4/3 because we changed the basis. So we changed the language actually. And our transition matrix, which is here, we will see how to compute it, is actually a dictionary. This will help us translate all the words that are expressed in standard basis, so all the coordinates in standard basis, into words or coordinates in the new basis. We will see how to construct this. It's not going to be complicated at all. Another example is if I have another basis for R2, 7, 2 and minus 2, 4, then the coordinates of the same point, 2, 2, will be here in this basis. Different basis, different language, different coordinates, different word. The dictionary is this one, so the transition matrix. It's different obviously because we changed the language. So English-Spanish is not the same in dictionary as English-Japanese. So this matrix is our transition matrix that helps translate every single word from one language to another. The good news about this matrix is it is invertible. So we are going to see how to build it and how to use it to translate words from one language to another or from one basis to another. So now we are going back to the board and start the lecture using numbers instead of a puppy. Everybody can understand the puppy, but apparently when you go for the words, it's a little bit more complicated. So what we want actually here is to answer 3 basic questions. So I'm gonna just write 3 basic questions to understand actually what we want in this section. So the 3 questions we want to answer. So question 1 is how to find coordinates of a given vector in a linear space in a given basis. So every linear space has infinitely many bases. So the question is, if I give you a vector v living in a linear space W, and I ask you find me the coordinates of that vector in a basis B1, how do you do it? So the first thing to do is to answer this question, how to find the coordinates of a vector v in a basis B1 of a linear space W. Okay. Obviously we can have many bases. We start with one and later on the process will be similar to another one if we change bases. So that's one question. And you will see it's very simple. Actually, what you need to do is solve ax equal b, so using our Jordan. Second question is an easier one actually, is given a coordinate or coordinates of a vector in a given basis, the question is, who's the guy? What's the vector? How can I find it? Well, that one is even easier to answer. So the question is, given the coordinates of V in a basis V1, find the vector V. You will see it's not complicated at all, very simple one. And the last question we want to answer is actually to build our dictionary, because all of these are just case by case and solution processes, but we can systematize everything. So in order to build a dictionary from English to Spanish, well, I'm going to build our transition matrix, and then all you need to do is give me a word in English, and this translation tool will produce a word in Spanish automatically. So that will be something fun to do and very easy actually. So the third question is how to build a transition matrix from a basis B1 to a basis B2. So that's the idea. So how do we do this? Again, it's going to be simple. This time, all you need to do is, again, apply Jordan, but on a special augmented system. So you have your new basis, B2, let's say. In our case, it's going to be B2, then slash, and our old basis, in our case, B1, and apply Jordan. So until when? Well, until you get identity on this side, and on the other side, you will get your transition matrix. So life will be very easy now. So let me try to illustrate how to do all this, one thing at a time. So we will start with the first objective is how to find coordinates of a given vector in a given basis. So if I change basis, coordinates will change. And then we will go to the easiest part, which is given coordinates, find the guy. And then we are going to build actually systematically a transition matrix between two bases. Obviously, if I change bases, I have B1 and B2, I'll get one transition matrix. We know that that transition matrix is invertible, so I can go from B1 to B2 using one transition matrix. The inverse of that transition matrix goes from B2 to B1. So you're going from English to Spanish, and then going from Spanish to English. It's just the inverse. So that's beautiful. What will be interesting is if I give you several bases, so B1, B2, B3, B4, then you will need to build a dictionary or transition matrix between each of these bases. So that's a little bit of work, but the process is always the same. So let's start with the first question. Given the guy, what are his coordinates in a given basis? And I'm going to start with vectors from R4 because I want you to understand that the coordinates in a basis have nothing to do actually with how many entries you have in a vector. So that's something important. And maybe a reminder, how do we know that a vector is in a linear space when we're given a basis? What do you need to do? So this is how you answer it pretty much. So given W subspace of R4 with bases, so plural. So let's take bases B1 and B2. So these are bases for W. And just to make things interesting, so first vector is 1, 2, 3, 4. Second vector is 0, 0, 1, 0. So this is one basis for W. And basis B2 for W will be 1, 2, 4, 4. Very creative. And 0, 0, 2, 0. Again, very creative. So W is span of B1, which is the same as span, of B2. Okay, cool. So that's my space generated by basis vectors, these and these, so it's the same space. Well, you can verify that this guy is a linear combination of these two guys, this guy also is a linear combination of these two guys, and the other way around. First guy from B1 is a linear combination of people in B2, and the second guy in B1 is a linear combination of people in B2. That will be your exercise to see if you remember how to do that. So I'm going to take a vector V, so very nice vector, 4, 8, 15, 16, so vector with 4 components. So first question is, okay, it belongs to R4, but does it belong to W? How can you know? Does V belong to W? How could you know that? What's the procedure? Well, we learned that a long time ago. If I want to know if vector belongs to a linear space and I have a basis for a linear space, well, all I need to check is, can I write the vector V as a linear combination of basis vectors? So this is the same as, can we write V as a linear combination of 1, 2, 3, 4 and 0, 0, 1, 0. Well, you could also ask the same question with these two vectors. Why? Because this is another basis for the same space. So actually, it's the same question, and the answer will be the same. If V belongs to W, then it's a linear combination of these two guys, and also it must be a linear combination of these two guys. Now, the good news is the coordinates are just the coefficients that we will get in front of basis vectors. So that's all it is. There is nothing else in it. So we have two basis vectors, so coordinates of V, if V belongs to W, will be A and B, two numbers, and that's all. So how do I find them? So to find the coordinates of V in basis V1, what do I need to do? Well, that's not complicated. I need to solve the equation A, so I'm looking for numbers A and B such that A times the first basis vector plus B times the second basis vector is equal to V, and V is 4, 8, 15, 16. So if I can find these two numbers A and B, then my vector V is a linear combination of the basis vectors, therefore it belongs to W, and at the same time A and B are the coordinates. So you can write like this: coordinates of V in basis V1 are A and B. This is A, not 9. Cool. How do I do this? Well, we learned that long time ago. What do I need to do? Well, I need to solve the system. What type of system? Ax equal b. Who's A, who's B? Let's write that. By the way, we are going to do the same thing, looking for the coordinates in basis B2. Not big deal. We know how to do it. So this means I need to solve the matrix system 1, 2, 3, 4, 0, 0, 1, 0, A, B equal to our monster 4, 8, 15, 16. So this is what I need to do. Well, you see that the solution has two components, so that's nice. Which means actually I need to solve augmented system. So I'm doing this once in my life, not twice. This has been done long before, so we know how to do it. This is just a reminder. So I need to solve this. Well, how do you solve it? Well, apply Jordan. Now the good news is, since, well, I know that this guy belongs to the linear space W, I'll have a solution. The good news is the solution is always unique if it exists. Why? Because these two guys are linearly independent, and from the theory, from your column space, row space, you will know actually that you will end up with two rows of zeros, and here you have an identity matrix. If you don't believe, you just do it. So I'll just dump you the solution. So just do the process, it's not a big deal. The solution is 4, 3. So the coordinates of vector v in a basis b1 are, so how do we write it? Well, some people write using square brackets, some round brackets, doesn't matter really. So that's what it is. These are the coordinates of vector v in basis b1. So you see, I have only two people in the coordinates. So my set of coordinates contains two guys, even though my vectors are from R4. So this way you understand that the coordinates have nothing to do with actually number of components or entries in your vectors. Okay? So dissociate these two things. That's why we give this example, so you can actually realize that coordinates are just numbers in front of basis vectors. That's all, nothing else. Good? So this is the same vector v we had at the beginning. What I'm going to do now is find the coordinates of the same vector v, so the same puppy, but in another language, another basis, b2. So that will be exactly the same process, but I'm going to use vectors from basis b2. So to find the coordinates, and again, these coordinates will be unique, of v in the basis b2 of w, so it's a basis for linear space. All we need to do is solve. So we had A, B, I'm just going to change letters. So it's going to be C, and what was the first basis vector in B2 was 1, 2, 4, 4, and the other guy I'm going to call it D, and the other vector was 0, 0, 2, 0, and my vector B was 4, 8, 15, 16. So it's the same guy, and I'm just changing basis vectors, and I'm looking for his coordinates in this new basis. What do? Well, not big deal. All I need to do is solve the matrix system. I'm going to write it again apparently. Okay. Which is the same as solving augmented system. Okay. So that's it. Need to find a solution. Well, good news. Somebody worked ahead and found the solution. Okay, so the solution for this thing, which means the coordinates. So how do we do? Again, apply Gauss Jordan. It's always Gauss Jordan. Chapter 1. Cool. Okay, so solution is CD, and it's equal to 4n minus 1 over 2. So that means that the coordinates of my vector v, the same bloody vector, in the basis B2 are, so I'm just going to clean this properly. So how we write it? Again, I'm going to write it with square bracket. You can use round bracket, it's up to you, doesn't matter. But you need to indicate the basis. So you see, it's the same vector, so same puppy, same word, but bases are different, so languages are different. Therefore, the words used for the same object will be different. So puppy in English is not the same as puppy in Spanish. Yet it's the same puppy. Hence the coordinates. So our vector was 4, 8, 15, 16. Basis B1 are what I already forgot, 4 and 3, and the coordinates vector, so the same vector. And the basis B2 are so 4, negative 1 over 2. So it's the same object but two different bases. How do I find coordinates in different bases? Well, I just need to solve the system Ax equal b, where matrix A has my basis vectors in column, and my vector B is actually the vector I'm having at hand, and the solution will be the coordinates. So that's not complicated at all, actually. Very simple. So now one simple question. If I give you a vector 0 from R4, what are the coordinates of vector 0 from R4 in our basis B1? Just for fun. So let's see that. I think many people will be happy to know that this can be solved easily. So question, what are the coordinates of the vector 0 of R4? So the vector 0, 0, 0, 0 in the basis B1. Then you guess the second question is, what are the coordinates of the vector 0 in the basis B2? So how do I find this? What do I need to solve? Well, I need to find A and B such that, so I need to solve simple system. So what are the basis vectors? 0, 0, 1, 0. This is what I need to solve. Well, this is homogeneous system. That's good news. Now, if you learned any theory before, you know when you have two linear independent vectors, because this is the definition of linear independence actually. So if you have two linear independent vectors and you want to find A and B for a homogeneous equation, well, the only solution is A equals 0 and B equals 0. Ha ha ha. It's useful to know your theory. Well, if you don't know your theory, you just solve. And then you'll be pleasantly surprised. So the coordinates of vector 0 from R4 in basis B1 are 0, 0. Oops. Ba-bam. Big miracle, huh? Well, guess what? The same coordinates are in B2. Why? Because the vectors that are in the basis of B2 are linearly independent, so the equation, the homogeneous equation will have a unique solution anyways. So this is just something that is obvious and trivial, but it's good to remember. Maybe another one. Another obvious one. What are the coordinates of first basis vector from B1 in the basis B1? Obviously, you can answer all these questions the same way you solve the system. So basis B1, we remember, is this guy, so, and this guy. So what are the coordinates of this guy in this basis? So what am I looking for? I'm looking to solve A 1, 2, 3, 4 plus B 0, 0, 1, 0 equal to 1, 2, 3, 4. So that's what I want to solve. I'm looking for A and B. To find them, well, you can do your Gauss-Jordan or be just smart and realize that if you put 1 here, and you put 0 here, you have your solution. Ta-da! So the coordinates for the first basis vector in the basis B1 are 1, 0. Simple. Now, what are the coordinates of the second basis vector of B1 in basis B1? Well, yes, what is 0, 1? So that is easy, and again, if you don't remember, you just solve the system. It's not a big deal. So that answers our first question, which is, give me a vector, and I'm going to find you coordinates of that vector in a given basis of a linear space. Just one thing, obviously if a given vector that I give you, because I'm evil, that one might or might not belong to the linear space. Well, how do you know? You try to solve the system. If the system doesn't have a solution, well, the guy I gave you doesn't belong to the linear space. So that one cannot have any coordinates in the linear space, obviously. Okay, so that's kind of obvious, but it's good to remind. So that was the first task. Given a basis, given a vector, what are the coordinates of a vector in that basis? Now the second task, which is much easier actually, is I give you a basis and I give you coordinates of a vector in that basis, and I ask you, what's the vector? So that's kind of obvious, it's easy. That's the second part. Given a basis and given the coordinates of a vector v in that basis, find the vector v. Example, again, our base is B1, or let's say B2. We haven't worked a lot with B2, so let's change a little bit. So B2, where are you? So 1, 2, 4, 4, and the second one was 0, 0, 2, 0. So this is my basis, and I give you coordinates of vector v in basis B2, and those coordinates, well, obviously they have two components. Let's say is -2 and let's say is 5, the other one. So the question is, what's v? So find v. Well, all you need to do is think for 2 seconds, and this says the coordinates of v are -2 and 5 in this basis B1, B2. So what does this mean? You just need to translate and you're good. This means that v is actually a linear combination of these two basis vectors, and the coefficients are -2 and 5. So coefficient in front of the first basis vector is -2. So I copy the basis vector. We change the basis just for fun, so we use the other one. Okay, so this is 0. To be cute, we are on TV. Okay, so all you need to do is compute now. So -2 plus 0 is -2, and -4 plus 0 is -4, and -8 plus 10, that's 2.